This tutorial will start backwards. I will first do a demo of the application to be built, and second, I will step by step write, explain, and run this application using an Eclipse IDE. Now, in this Java 8 genetic algorithms application, I will have each city identified by its latitude and longitude coordinates, and I will be using the Haversine formula to calculate distances between cities, and the application will find and display the shortest route found. This is a pre-built version of the application that I will be using to do a quick demo. So we go from generation 0 to generation 29, which I specified as the maximum number of generations. And each generation has a population of 8 routes, with the shorter one being this one. So I am sorting by fitness. This is the highest fitness, which means the shortest route in miles. And we evolve from one route's generation to the next by doing selection, crossover, and mutation, and also including the use of elitism. And this was the best distance in generation 0, and in generation 29 this is the best distance. So the best route found so far is this one with this distance. Next, let's go ahead and create a new project. It will be running on Java 8. And here I will have a city class representing a city in the route, and it will be in this package, and a route class representing a route candidate solution, which will be starting at one of the cities, passing once in every city, and then returning to the originating city. And we will have a population class representing a population of routes, and a genetic algorithm class where the selection, mutation, crossover, and elitism logic will be. And we will have a driver class with a main method. Now going to the city class, it will have a longitude and a latitude and a name, and get methods that would return the longitude, the latitude, and the name, and we will initialize them in the constructor. So it will take a name, a latitude, and a longitude. And let me define those three constants. So the Earth's equatorial radius, and converting degrees to radians, and converting kilometers to miles. And I'll have the toString method returning the name of this city, and we will have this measure distance method that measures the distance between this city and the past n city. So for now, let's return 0. And I'll first calculate the delta longitude and delta latitude. So the past n city dot get longitude minus this city dot get longitude. And we will use those deltas in this formula. So pick up A by doing this and passing in here the delta latitude, and we're passing in here the delta longitude. And I will return the distance between the two cities in miles. So this is A that we calculated here. So in short, this method uses the Haversine formula to calculate the distance between the past n city and this city. Next, going to the route class, we'll have an array list of cities in this route, and a get method that returns those cities, and the toString method will print out the cities in this route. And I need a method that calculates the total distance in this route. So let's return 0 for now. And we also need a method that determines the fitness of this route. Let's also return 0 for now. And we will have a constructor that initializes the list of cities, and shuffles them afterwards. And here in route, I will define this flag is fitness changed and set it initially to true. And I need to keep track of the fitness, so I'll have this fitness and set it initially to 0. And when the getCities method is called, it's possible that fitness will be changed. So is fitness changed is true, and in getFitness I will return the fitness, but before doing that I will check if the isFitness changed flag is true, and in that case I will recalculate the fitness and set isFitness changed flag to false. So here I have the fitness calculated as 1 over the calculate total distance method, so we call this method. So 1 over that, and for convenience I'm multiplying by this number. And now for this method, Let me first pick up the cities size, so the size of this array list, so how many cities it contains, and we will use Java 8 to sum up all those cities. So we use measure distance method on the city class to calculate the distance between city 1 and city 2, and then city 2 and city 3, etc. And then summing them up and adding the distance between the last city and the originating city. So we add right here. We do this dot cities dot get 0, so the initial city, and we measure the distance to the last city. Next, going to the genetic algorithm class, we define this population size. So this is the number of routes in a generation, and now in the population class I will have an array list of routes set to the size that we just set, population size. And let's have a get method that returns the routes, and I will use Java 8 to sort the routes by their fitness, and we need a constructor that initializes all the routes given the population size. So we're using range from 0 to population size, and then for each, and we're adding a new route instance given the passed in array list of cities. And if we go here, we end up shuffling those cities in that array list. Now going to the driver class, we define this array list initial route, so it contains cities with their latitude and longitude. And going to the genetic algorithm class, I will have this initial route that is initialized through a constructor that will end up being called from the driver class, and we will have a get method that returns that initial route. And now going to the population class, I will have this constructor, and in the route class I will have this constructor that takes in a genetic algorithm, and here we're adding nulls to the cities array list. So now we are done with the city class, with the route class, and with the population class. So what's left is the genetic algorithm and driver classes. And here let's add this mutation rate, and this is the probability that a chromosome gene will do random mutation, and the range is between 0 and 1, and is usually small. Now, for the traveling salesman problem, a chromosome is a route, and a gene means a city in that route. And here I will be using tournament selection to do crossover. So this is tournament population that is used for the route crossover selection, or for the chromosome crossover selection. And I will specify the number of elite routes to be 1, and elite routes will not be subjected to crossover or mutation from one generation to the next. And we will have 30 generations, starting from generation 0 and going to generation 29. Now here we will be applying crossover to the population. So we'll have this crossover population method, and for now let's just return null. And also we will be applying mutation to the population of routes. So for now let's just return null, and we will have a public evolve method that will apply those crossover and mutation to the passed in population. And crossover population will end up calling this crossover route method. Let's return null for now. And route 1 and route 2 are obtained here using tournament selection. So let's have this method that returns a tournament population. And let's return null for now. And mutate population will end up calling this mutate route method. So let's return null for now. Now here we will instantiate a new population given the size of the old population, and passing in this genetic algorithm instance. And we will return that new population, but before doing that we will move the elite chromosomes as is, and here we only have one elite chromosome, since we have this set to 1. So we will use the range method on endstream, and then do for each one of those elite chromosomes, we will put it in the crossover population as is. And for the remaining ones in the old population, so we'll start from the number of elite routes, and go to crossover population dot get routes dot size, and we will use tournament selection to pick up 2 routes. So we do select tournament population, and then we pick up route 0 in there, which should be the fittest route, since we are sorting by fitness. And we will call the crossover route method that we haven't coded yet on those two routes, route 1 and route 2, and we obtain a new route that we will set in the crossover population routes. Now for the mutate population method, we will keep the elite routes as is. So I'm filtering them, since I will return same population past n. And for each one of the non-elite routes, I'll call the mutate route method on it. Now for the mutate route method, this is an example of what this method should do. So say this is the original route, and after calling this method on this original route, we end up with this mutated route. So for example, those two ended up being the same. Now for LA and New York, we switched those in the mutated route, and then Seattle stayed the same, and we switched those two, Chicago and San Francisco, and those two stayed the same. So this is the code that does that. So here we do a filter. If mass.random is smaller than the mutation rate that we define over here. And this code picks two cities and flips them, and we return the mutated route. Now for this method, I have a tournament population, and the tournament population size that we specified here is 3. So there will be 3 routes in a tournament population, and let's return this tournament population. But before doing that, I will randomly select a number of routes, and then actually before returning them, let's go ahead and sort those routes by fitness. And in the method crossover population, we are picking the fittest one, so get 0. We have route 1 and route 2. We do another select tournament population call, and we do get 0 also. And now for this crossover route method, an example of what this method will be doing. So a crossover of route 1 and route 2. So let's say this is route 1 and this is route 2, and we want to do a crossover of those 2 routes. So an intermediate crossover route will be, for example, picking those routes from route 1. So we have those 5 cities, and filling the remainder with nulls. And then from route 2, we will be filling those nulls. So the final crossover route will contain those 5 routes, and for the first null we go to route 2 and we check if LA is in here, and it is not, so we add it. And then we check if Seattle is in here, and it is not, so we also add it. And for the third one we check if Austin is in here, and it is not, so we add it here. And then we check if Boston is in here, and it is, so we skip it. We check if Denver is in here, and it is not, so we add it. And we check if New York is in here, and it is, so we skip it. Houston, the same thing, we skip it. And Dallas is not in here, so we go ahead and add it. So we end up with this final crossover route. So I need a method that goes from this intermediate crossover route to this final crossover route. So I will have this method, fill nulls in crossover route, and I'll pass it the crossover route like this one here, and this route will be route 2 in this case. And for now, let's return null. And for completeness, an example of what this method does is if we have this crossover route with those nulls, and this route passed in here, we end up with this crossover route. So here I will be returning this crossover route for convenience, but before doing that, this is the code that would achieve this functionality. So I'm using the filter method here, and I'm checking if the crossover route that getCities that contains X, if not crossover route that getCities that contain X, then I'll go ahead and do for each. And I have a for loop where I set the city and then break out, and then do the same thing again. So we are running for each here. So we will be calling this method from the crossover route method. So here I'll have a crossover, actually let me call it crossover route, and temp route 1 is route 1, and temp route 2 is route 2, and we will be returning a call to this method with the crossover route and temp route 2. But before doing that, and since we are randomly doing crossover, if I'll have a mass.random smaller than 0.5, then I will switch those. So temp route 1 will become route 2, and temp route 2 will become route 1. And this call will fill up the intermediate crossover route. So crossover route.getCities.set. So temp route 1 dot get cities dot get one of the cities. So this should do it for the genetic algorithm. So we did the evolve method and the crossover population and the mutate population and the crossover route, which end up calling this fill nulls in crossover route, and the mutate route method, and the select tournament population method. So next we will be writing the driver class. So I'll pick up a driver instance, and a population, passing in the initial route and the population size, which we specified here to be 8. And before doing anything, I'll sort the routes in that population. So sort routes by fitness. And I need a method that prints that population. I'll have this print population method where I would pass it a population of routes, and it will pick up the routes and then do a for each and print out the cities in that route and the fitness for that route and the distance for that route. So let me go ahead and call that method from main, and let's test run it. Here we go. So this is generation 0, and we have 8 different routes, and this is the fitness for each, and this is the total distance for each route. So this was generation 0. So I'll have this int generation number, and we'll start from 0. And I have a varied number of cities here. So the array that contains those cities is going to be different. The size of that array will be different when we print it out. So what I need is to be able to print the heading given the variable size of that array. So I'll have this method print heading, where I would pass it a generation number that it would print it, and it would be able to print for any number of cities. So if I change here, I only have 9 cities, it should be able to print for those 9 cities. So let me call it from here, driver.print heading, passing in this generation number. So if I test run it, we have the route and ends here, given the size and the fitness and the distance. So let's go back to 10 cities. And run it again. and it is able to handle it. So only the size of the route column would change by changing the number of cities. Those two would stay the same. And this is what this method does. And next we need to evolve from generation 0. So let me have this genetic algorithm instance passing in the initial route. And I need a while loop where we would be evolving that population given the number of generations that we defined over here. So for each new generation, we'll print the generation number, and then we will evolve that population, and sort the routes in that population by fitness, and then print the population in that generation. And the best route we obtained will be route 0, given that we sorted those routes. So population.getRoutes.get 0, and let's also print the total distance for that route, population.getRoutes.get 0, and calculate total fitness. This would be in miles. So this should do it for main. Next, let's go ahead and test run it. So we went from generation 0, where the fittest route had a distance of 10,352 miles. And we went to generation 29, where the fittest route had a distance of 7,553 miles. So this is the best route found so far. So we go from Houston and we pass through all those cities, and then we come back to Houston from Seattle. And actually let's do another and see what we get. So we actually went down. Got a better distance. We started from this distance. And I want to compare this against the exact best distance. So we can obtain that using the brute force code that I've done previously. So let's make sure I have the same cities. Let's copy those from here. And go to the driver in brute force. We will have the exact cities, exact same cities. let's run it. So we have a 10 city tour, and the best distance is 6,977, and this is the best routes.